All right. We got another cool one based on the same reference problem here. So we'll actually reference the last question as well. So for our statement, we have repeat problem 19, but this time let the external force be a Dirac delta function. F of t is equal to k delta t for some constant k. Note that acceleration is now discontinuous at t equals 0, though the velocity must still be continuous. Use the method of 11.19a to show that delta a is equal to negative k over m tau. In this problem, there are only two intervals to consider, less than 0 and greater than 0, thanks to the external force being a Dirac delta. Check that the energy is conserved in the process, hence what we had to show last question. All right? So with that being said, the equation of motions can be rewritten. We have A equal the radiation reaction, so tau A dot, plus F over M. But here, F over M is at Dirac delta. So we have dV dt is equal to tau dA dt plus K over M Dirac delta. Okay? So if we're applying the same method, then we see that we have dV dt with the integral from negative epsilon to epsilon. So, apply that same integral to everything. And clearly we see that the Dirac delta just makes that go to 1, so we don't care. But we have V E epsilon minus V negative epsilon is equal to tau A epsilon minus A to the negative epsilon plus KT. Velocity is continuous, so we have V epsilon is equal to V of negative epsilon, so the left-hand side is 0. And if that's the case, then we have to take into account that Km term needs to go to the right-hand side, so we minus that over and then divide by tau. So what this is actually saying is that the difference in the A's is actually negative K over M tau, or we're going to say delta A. So cool there. So for t less than 0, A is equal to tau A dot, so then we get the equation of motion for that. When t is greater than 0, we have a similar equation of motion. AT is equal to beta t over tau. Again, very similar here. And now we can use the fact that delta A, which is equal to A epsilon minus A negative epsilon evaluated at t equals 0. Now we can find out what A and B are as far as the coefficients. And so we see that with that, B is equal to A minus K over M tau. And so our general solution looks like such, where for t less than 0, we have A e to the t over tau. And then for t greater than 0, we have the acceleration is A minus K over M tau bracket all times e to the t over tau. So if we want to eliminate the runaway region, we have to have A equal K over M tau to get rid of that second part, or t greater than 0. Again, that's the same method that we used last time. So our final set of equations for acceleration is K over M tau e to the t divided by tau for t less than 0. So we just have a pre-acceleration region. Okay, clearly we cannot have both. So once we eliminate that, then we could solve for v by taking the integral again. So we do that from negative infinity to t of at prime d prime t, or dt prime. We just can't have the same integral or same value, or not variable. That's what I wanted, variable. Okay, so here k over m tau is a constant, move it through, and then we're just left with e to the t prime over tau. Again, a pretty easy integral in my opinion. And we're left with k over m e to the t divided by tau. Since that factor of 1 over tau cancels with the integral and the integration tau. Again, for t less than 0. And if we want, again, v has to be continuous at 0, so we just have to add this through. And we see that we're just left with v naught after the integration, since acceleration there is 0 in the region from 0 to t for t greater than 0. So v of t is equal to v naught, which we just say is equal to kt. Okay, at t equals 0, that makes sense. Similar to what we had last time. So the velocity is that piecewise function. Nothing crazy in my opinion. So with that, for an uncharged particle, we would just do the same kinematic relations and find that V is equal to 0, K over M. So nothing too absurd in my opinion. But here, B, the external force, the energy of the external force, the work done by the external force, F dx, we use the same method as in the last question and chug it through. So we get K times V naught, and that's equal to K squared over M. Okay, cool. Easy enough to deal with. And then kinetic is 1/2 mf squared, 1/2 mvf squared. So we know that that's K over M. M's cancel again, so you get K squared over 2M. With radiation, we know what to expect. With the Lamar formula, square that acceleration. Carry out the constants. No biggie, no biggie. Again, read through the math carefully as things tend to cancel. And with that, we end up with a K squared over 2M. So does the kinetic energy plus the radiation energy equal the external force? Well, we get K squared over 2M plus K squared over 2M. Does that equal K squared over M? Well, sure does, because then you get 2K squared over 2M and the 2's cancel. So you're left with K squared over M. That's pretty darn cool. Before we finish, let's go take a look at these graphs. So for the acceleration, we know that we got rid of the runaway region. Okay, so anything to the right of 0 should not exist. And that's what we see in our acceleration graph. The charge does have a pre-acceleration region, but you see the neutral has just the Dirac delta that happens at the origin, hence the dashed line. But the charged particle has that pre-acceleration region. It's pretty weird to think about. Now for the velocity, we know that we should just end up with a constant velocity of K over M. But again, that charged particle has that pre-acceleration region. So we accelerate up and then we go to a level at 0. Whereas neutral, you just hit, at 0, we hit the spike thanks to the Dirac delta. But, similar question, but pretty darn cool. And I'll have some more words for you in the description.